Hello and welcome to a little dose of magic, a little nugget of learning in support of stats magic. We're going to talk about dice. This pairs well with the coin toss, as well as Lecture 1 from Probability to Statistics, as well as Roll Up the Rim. We're talking about dice rolling. Everyone knows that when you roll the dice, the chances are 50-50. Ha! No, not really. There are 6 possible outcomes, and each is equally likely. This is the universally accepted fair way to determine who gets the biggest number. It's the mechanism behind many board games, the source of skepticism and betrayal amongst board game players. And just like the coin toss, we're making assumptions already without even realizing it. We assume that this dice has an equal chance to land, showing each of its 6 faces. But here, in this mini experiment, after our first toss, the proportion of our data is either 100% it's a 6, or it's 100% not a 6. We know that there's other options, but we will only see one in a roll. That means truthfully, it's 100% a 6, or it's 100% a 5, or it's 100% a 4, or it's 100% a 3, or it's 100% a 2, or 100% it's a 1. If we toss again, we have the exact same situation. It will either be 100% a 6, or 0% it's a 6, which we know is actually 6 different options. But now, with the second roll, we know it can be another number. This gives us 36 equally likely total outcomes. You could get a 1 first, and then you can get 1, 2, 3, 4, 5, and 6 in the second roll. You can get a 2, 3, 4, 5, or 6 in the first roll, and get a 1, 2, 3, 4, 5, or 6 in the second roll. 36 possible outcomes, all equally likely. All faces of the dice are equally likely, but it is not equally likely to get a 6 or not get a 6. What's more, when we roll the dice 6 times, it could be all over the place and not close to 1 out of 6 at all. So for counting frequency, the number of occurrences of each outcome, we could try rolling the dice 10 times. And when we do, we get 5, 2, 6, 1, 2, 5, 4, 6, 5, 2. That's 1, 1, 3 2s, no 3s, 1 4, 3 5s, and 2 6s. This looks like a mess. It doesn't really look like any shape at all. If we ramp up the numbers, 10 is great, 100 is better, we get a little bit more even. This is 100 tosses from a random dice roll simulator that I found online. It's starting to look flatter, but it's not perfect. So here we go. We know that a probability distribution for a dice roll should be completely flat, especially from a dice roll simulator, because it is literally based on completely flat. The more rolls that we do, the closer we are going to get to this probability distribution, but a completely even divide on actual dice rolls is not very likely. So how likely is it then? It's not very likely to get a completely even split, and it's much less likely to get all 6s. But let's see if we can graph this. We counted frequency, we made a probability distribution, but this still brings us back to a single dice roll. 1 out of 6 for each face. How likely is it to get 2 6s? We know that there are 36 possible combinations. Only 1 has 2 6s. 10 have 1 6. The rest have none. So we can do this sets of 2 100 times. And if we plot it, it ends up looking like this. That's strange. If we increase the number of repetitions, so we have 1,000 double dice rolls, then it would look closer and closer to this theoretical ideal based on what's possible. But this still looks weird. The coin toss, I demonstrated smoothing of the distribution by increasing the number of flips from 2 to 3. It showed that increasing the number smoothed out the curve and started to make it look a bit more like a ghosty. But when we do this here with the dice roll, this just looks more weird. It looks like half of a distribution. Now there are 6 options. You can't even see all 6 of them if you wanted to if you're only rolling the dice 3 times. So we need to roll the dice more per trial. So let's try rolling the dice 10 times, and we're going to do that 10 times. Well, now you see in the histogram of getting 0, 1, 2, 3, and 4 6s, it's starting to have a bit of a curve to it. It is still possible to have more than 4, but we didn't actually see that. Again, this is made with a dice roll simulator. Now, what if we did 10 dice rolls 100 times? Well, now we're getting somewhere. This is starting to look a little bit more normally distributed. Again, it is possible to have more than 4 6s when you're rolling a dice 10 times, but it is very unlikely, so we didn't actually see it in our simulation. Now, eventually, with enough dice rolls in a sample, and enough samples to make the proportions consistent and reliable, we should eventually end up with something like this. And unlike the coin toss, which centered around 50-50, now we are centered around 1/6, which is 16.666 repeating 6s. It's still a ghosty. Ba-ba-da-ba. So we went from 1 and 6 to 100 or 0, and then we did some weird charts, and now we're here. We have this ghosty that's centered around 16.666 repeating percent 6s. Why did we do this to ourselves? Well, I still don't know, but at least it's honest. The probability of rolling a 6 is still 1 out of 6, but you are unlikely to actually realize in perfect numbers 1 out of 6. You're more likely to see 1 out of 6 than any other possibility, but it's still just one of many chances. But now we can see that getting 2 6s and in 3 tosses will come in around here. And getting 2 6s in 10 rolls is going to come in around here. Much more likely to get 2 6s in 10 rolls than it is to get 2 6s in 3 rolls. And that makes sense. And that's it. Thank you.